Hello everyone, welcome back to Xcoding with Alvian. In this video tutorial, we'll be learning on how to build a serverless REST API using Swift as the language. It will have several endpoints to create, read, update, and delete Todo Items. We'll use AWS DynamoDB to persist our data in the cloud. Then, to deploy, we'll be deploying to AWS Lambda using Serverless framework. Along the way, we will learn on how to use Swift AWS Lambda Runtime and AWS SDK library. And finally, we'll be learning on how to build and package our Swift app using Docker and official Swift Amazon Linux 2 image. So, without further ado, let's begin our learning and coding. So, before we begin, let me show you the completed application that we will build. As you can see here, this is the AWS Lambda console. In here, we have 5 functions: delete, create, read, update, and list. And if you see, we are using API gateway as the trigger. It means we are going to use HTTP to trigger all of these functions. And this is the DynamoDB console. And this is a sample iOS app built in Swift UI on core data to perform a CRUD operations. As you can see in here, we already have about 6 items here getting displayed in the mobile app. And from the mobile app, I can update a function, a to-do item. I can create a new to-do item. It should get added to DynamoDB here. And I can also delete the to-do item. So this is basically the app that we will build in this tutorial. So let's begin. Before we begin our tutorial, let me give you some information about AWS Lambda. Let's open our browser and visit AWS Lambda website. We'll be deploying our Swift code to AWS Lambda. It is one of the most popular services that let us to run code without provisioning and maintaining the servers by ourselves. We just need to pay for the compute time we use to run our code. Also, the code will be executed using event-driven paradigm that can be triggered from various sources, such as HTTP requests via Amazon API Gateway, modification to objects in Amazon S3 buckets, table updates in Amazon DynamoDB, and many more. It provides flexibility for developers to provide their custom runtime to run on Lambda. We're going to use this custom provided runtime to package our Swift executable and deploy it to the cloud. Currently, AWS and Azure are 2 of the top cloud services that provide the capability for using custom runtime to execute a function. Last month, before the WWDC, the Swift core team and Swift server workgroup had announced the availability of Swift AWS Lambda Runtime as well as support of Swift running on Amazon Linux 2. With both of these announcements, we finally have some official support to run Swift on AWS Lambda environment. Swift has many advantages such as low memory footprint, high performance, and quick start time. The Swift AWS Lambda Runtime also uses Swift Neo to provide high-performance, non-blocking networking engine, so we can run asynchronous event-driven code. The runtime itself provides built-in support for many Lambda-supported events, such as HTTP request event from API Gateway, S3 bucket storage event, simple notification service, and simple queue service. Okay, I think that's enough for the background introduction of AWS Lambda and Swift Lambda Runtime. I'll provide the link in the description if you want to learn more about them. Now, let's begin to create a new Swift project and build the Todo Service API app. Let's begin to create a new Swift project and build the Todo Service API app. First, let us open the terminal, navigate to your favorite directory, and create a new folder named Todo API and navigate into it. And inside this folder, we're going to create a new Swift package with the type of executable using this command: Swift package init -- type executable. It should create all the files. If you are using Mac OS, let's open the Finder and double click on the package.swift file to open the project in Xcode. If you are using Linux, you can use your favorite text editor to follow along. It won't have the code completion though. Let's add the required dependencies for our backend app. Open package.swift file from the navigator. Let's add the platform first. In our case, we add Mac OS version 10.14. The first dependency we need to add is Swift AWS Lambda Runtime package, provided by the Swift server workgroup. Currently, the version is 0.2 and it's in pre-release stage. So let's add it. The second dependency is the official Swift AWS SDK. This package provides native Swift API for us to interact with various AWS services, such as DynamoDB, S3, and many more. This package is created by AWS. We're going to get the latest one, which is 5.0.0 alpha.4. Okay, let's move on to the target. In our main target, we need to add 3 dependencies. The first one is AWS DynamoDB from AWS SDK Swift package. The others are AWS Lambda Runtime and AWS Lambda Events from Swift AWS Lambda Runtime package. Make sure to save the file using Command +S shortcut. This will download and resolve all the dependencies. You can view the progress from the dependencies section on the navigator here. After all the packages has been downloaded, try to build and run to make sure there is no build time error. Make sure to select My Mac here. Okay, so let's explore a bit on how AWS Lambda Runtime library handles the function invoked. Let's go back to the website from swift.org. If we can see in here, how does it work? The first one is to use closure or callback. In this example, the request payload is a string. It can be also a JSON that conforms to a decodable protocol. And maybe various AWS events, such as in this case SQS, or it can be S3 or API gateway request. So we need to make sure to invoke this callback, passing the response that we want to return in the function. The second one is to use the event loop Lambda handler, which is more suited to performance sensitive function. In this case, the function will run in the same thread as the networking handlers. So no need for performance cost penalty because of context switching between networking and processing threads. It used Swift Neo even loop primitives. In this case, our handler will return the even loop. If you are familiar with JavaScript, the even loop concept is very similar to promise, which means the value will be resolved later in the future. We'll be using even loop Lambda handler to build our REST API using the API gateway handler. Let's create the model for the to-do first. Create a new directory named models. Then create a new Swift file named to-do. Then let's create a to-do struct that conforms to codable protocol. It has 6 properties: ID as string, name as string, is completed as boolean, and do that, created that, updated that as date. Also, to help us later when writing the model to DynamoDB dictionary, let's create a nested struct named DynamoDB field inside the to-do struct. In this case, we just need to provide the keys for each of the property using a static constant. Let's create a new file named utils.swift. We'll use this to store the date formatter using ISO axis01 format using the static constant. As DynamoDB does not provide support to store date as the data type, we need to convert the date to the ISO string using the formatter and store the date as string. Below the struct, let's create a simple extension for date. So we can convert the instance to ISO string using a computed property. We just need to use utils date formatter to convert the date using the string from date method, passing self as the parameter. Next, create a new file named APIError. We declare the APIError as enum that conforms to Swift error protocol. Let's declare 3 cases: decoding error, request error, and to do not found. Next, create a new file named todo plus DynamoDB. In this file, we'll create an extension for todo that will help us to convert to the instance to DynamoDB dictionary. This will be used when we want to create an update item into DynamoDB. Make sure to import AWS DynamoDB at the top of the source file. The dictionary uses string as the key and DynamoDB attribute value. We'll use the DynamoDB field constant that we have declared before inside to the struct as the key. Then we can initialize DynamoDB attribute value instance passing the correct data type. For string, the parameter will be s, and for boolean, it will be bool. We may also make sure to convert our dates into a string before we put it into the dictionary. Next, we also need to create an initializer that accepts DynamoDB dictionary to initialize a to-do instance. This will be used later when we retrieve to-do items from DynamoDB SDK. In this case, using the guard statement, we make sure all the properties exist in the dictionary and can be casted to the actual data type before we assign them to the properties. If one of them is not exist or the data type is incompatible, we throw a decoding error. That's it for the models. Let's move on to create a to-do service. This service has the responsibility to interact with AWS DynamoDB SDK, to get list of items, and also to read, create, update, and delete a single item. Create a new file named todoservice.swift and I import AWS DynamoDB at the top of the source file. Declare todoservice class will need two instance properties. First is the instance of the DynamoDB itself. The second one is the table name of the to-do item in AWS DynamoDB. We create an initializer to inject those two properties. Next, create a new method named getAllToDos that returns an even loop feature of to-do array. We need to create the DynamoDB scan input instance passing the table name. Next, we can use the DynamoDB scan method passing the input. We're going to change the scan output to todos array using the flat map throwing operator. If you are familiar with JavaScript promise pattern, you can think of this as the then operator. In case of this, as the mapping can throw an error, we need to use the flat map throwing operator. There is also the normal flat map operator. For creating to-do, create a new method named createTodo with a single parameter of to-do model. The return type is event loop feature of to-do. In the implementation, we copy the to-do struct to a new variable, then initialize current date. Then we assign the updated at and created at property with the date. Next, we create a DynamoDB put item input, passing the to-do DynamoDB dictionary using the computed property we created before, as well as the table name. At last, we invoke put item method on the DB, passing the input. In this case, we can just return the instance of to-do using the map operator. For updating to-do, create a new method named updateTodo with a single parameter of to-do model. The return type is event loop feature of to-do. Create a new variable to copy the to-do struct instance. Then we can just assign the updated at with the current date. Implementation of update item input is quite complex compared to the create item input. We'll need to create the expression attribute names array containing the keys we want to update. Then we create the expression attribute values array, which are the values we want to update. Pass the key, which is the ID, then the return values to all new. Then we have to make sure to pass the table name, and finally we need to use the update expression literal, passing the placeholder attribute names and values we have created. At last, we can use the update item passing the input. Then, using flat map, we invoke the get to do item passing the ID to return an event loop feature of to do. At last, to delete an item, we need to create delete to do method passing the ID of string as single parameter. The return type of this will be an event loop feature of void. In the implementation, create the DynamoDB delete item input passing the key and table name. At last, we invoke the DB's delete item method passing the input. Using the map, we return a void closure. That's it for the to-do service. With this, we'll be able to perform CRUD operation to DynamoDB. Let's move on to create our Lambda handler. Create a new file named TodoLambdaHandler. We need to import several frameworks into the source code. First, let's declare the TodoLambdaHandler as a struct that implements event Lambda handler protocol. The protocol itself uses associated type for the event input and the response output. In our case, we're going to use API gateway request for the input event and API gateway response for the output. There are several other options you can explore, such as S3, SNS, SKS, or DynamoDB. The handler itself needs to have reference to the DynamoDB instance and to the service instance, as well as HTTP client used by DynamoDB. Let's declare this as the instance properties. Next, we need to create the initializer that accepts the Lambda initialization context. Basically, we need to initialize the DynamoDB instance and to the service inside the implementation. First, let's create HTTP client and instance. We need to pass this when initializing DynamoDB later. Declare the timeout variable and initialize it with HTTP client configuration timeout. We pass 30 seconds to both connect and read parameters. Let's declare the HTTP client variable and initialize it, passing the .shared with the current context event loop as the event loop group provider. Then for the configuration, we initialize HTTP client configuration, passing the timeout variable we created before. Next, we need to retrieve the name of the table for our DynamoDB Todo item. We'll be storing the table name, AWS underscore region, and handler as the environment variables when we deploy our function to AWS later. To retrieve the environment variable, we can use lambda.env static method, passing the name of the variable we want to retrieve from the environment. First, declare the table name constant and pass the string of todos underscore table underscore name as the parameter. For the region, we pass AWS underscore region as the parameter. Then using the value, we initialize the region enum, passing it to the value parameter. If it doesn't exist, we provide a default fallback region, which is US West 2 at Oregon, US. Next, we need to initialize the AWS DynamoDB instance. Declare the DB constant and using DynamoDB initializer, we pass the region and the HTTP client provider as the parameter. For the Todo service, we can initialize it, passing the instance of the DB and the table name. At last, we assign all the properties into the instance variables so we can reference to them later. That's it for the initializer. We have the DB instance and Todo service to perform the CRUD handling operation inside the handler. There is one required method we need to implement. It acts as the entry point when handling the request into our app. It is handle context event that returns an event loop feature. This will be invoked passing the context and the request API gateway event containing the HTTP payload. The return type expected is the event loop feature API gateway response, which is the representation of the HTTP response we want to return to the client. As we are going to use single binary to perform all the CRUD operations, we need to be able to know the type of the operation we need to perform when the user hits our app. To do this, we need to create an enum named handler. Basically, this enum represents all the supported operations in our app. Create a new file named handler inside model folder. Import AWS Lambda Runtime at the top. Then declare the enum handler with type of string. Our API supports 5 different operations: create, update, delete, read, and list. To get the handler value, we'll declare a static computed property named current that returns the handler. We'll retrieve the handler from the environment variable name underscore handler. We will set this environment variable for each of the operation when we deploy our functions later using serverless framework. Before implementing the handler, let's create a helper extension for the API gateway request and response. That will help us to decode and request into the model and encode the model into the response as JSON string. Create a new folder named extensions, then create a new file named API gateway plus extension inside. Import foundation and AWS Lambda events. First, let's declare the extension for the API gateway request. We declare one helper method that will help us to decode the JSON body of our request. to decodable type using generic placeholder. Before that, let's declare the JSON decoder static constant and set the date decoding strategy to custom formatter, passing the ISO x601 date formatter from the Utils. In the body object implementation, using the guard let statement, we check whether the body data exists. If not, we throw a request error. Then, using the JSON decoder, we just decode the type passing the JSON data. Finally, we just return the decoded instance. Next, let's create the helper extension for API gateway response. Let's begin by declaring the JSON encoder static constant. Similar to the JSON decoder, we set the date decoding strategy to use custom ISO date formatter. Next, let's declare the constant for the default headers. The value itself is a dictionary with type of string as the key and value. This will be used to set the HTTP response headers to allow cars when invoked from our website and to allow all HTTP methods. Let's move on to create a new initializer that accepts error and AWS Lambda events HTTP response status. Let's move on to create a new initializer that accepts error and AWS Lambda events HTTP response status. In this case, we just invoke the default initializer passing the status code, then pass the default headers as the headers parameter. Also, in the body, we pass hard-coded JSON string with key of error and string value of the error. We'll use this later when we want to return an error as the response. The second initializer accepts an encodable object using generic placeholder and the HTTP response status. This will be helpful later when we want to return instance of to-do or to-do array, as they both conform to encodable protocol. In the implementation, we encode the instance using the JSON encoder and assign the string of the data to the body variable with UTF-8 encoding. At last, we invoke the initializer, passing the status code, the file headers, and the body. At the bottom, create a new struct named empty response that conforms to encodable. The implementation is empty, as this will be used when we want to return a response with empty body, such as when deleting a Todo item. Finally, let's move back to the TodoLambdaHandler to implement all the handlers method. Let's go back to the TodoLambdaHandler.swift file and insert this handle method. First, let's use a guard statement to get the current type of the handler operation using the handler.current static property. If it is not exists, we just return our result for a successful event loop feature, passing the API gateway response instance with APIError and bad request HTTP status type. This will returns the response with 400 as the HTTP status code containing the error message in the body. Then, we use the switch statement on the enum instance to handle all the possible operations. We'll create a method to handle each of the operation, all of them except Lambda, context, and API gateway requests as the parameters. Then returns event loop feature of API gateway response. First, let's declare the handle CRUD method to handle creating a single to-do item. Using the guard statement, we decode the request body to the to-do instance. If it doesn't exist, we return a resolve event loop feature passing the API gateway response of request error and that request HTTP status. Next, we invoke Todo Service create to-do method passing the to-do instance. As this returns a feature of to-do, we need to map it to API gateway response using the map operator. In the closure body, we initialize the API gateway response passing the to-do instance and OK as the HTTP response status. This will encode the instance into the JSON data, then put it in the response body and set the HTTP status code to 200. Also, in case there is an error in the event loop chain, we need to catch it and return the appropriate error. Let's declare a method named catchError that accepts a Lambda context and error as the parameter. Then return the event loop feature of API gateway response. In the body, we just need to initialize the API gateway response and pass the error. Then return the resolve feature passing the response. Going back to the create method, to catch the error, we can use the flat map error operator. This will be invoked if there is an error thrown in one of the upstream chain. Think of this as the catch error promise in JavaScript. In this case, we can just invoke the catchError method we created earlier to return the API gateway response. Next, let's create the handle_ref method. In the implementation, we check if the path parameters dictionary contains a value with key of ID. If not, we just return a resolve promise of response with request error and HTTP status 400. Then, we just need to invoke Todo Service getToDo method passing the value of ID. Using map operator, we transform the to-do instance to response, passing the to-do instance to be encoded in HTTP body and set the status code to 200. Don't forget to catch the error using the flat map error. To update a to-do item, let's create the handle update method. Just like the handle CRUD method, using the guard statement, we decode the HTTP body to the to-do instance. If it fails, we just return our resolve promise with response containing request error and HTTP status code of 400. Then, we invoke Todo Service update to-do method, passing the updated to-do item. Using the map operator, We transform the result of todo item to API gateway response, passing the todo instance to be encoded as JSON in the HTTP body and set the HTTP status code to 200. Next, let's create the handle delete for deleting a todo item. Just like the handle read method, we need to get the ID to delete from the path parameters dictionary, passing ID as the key to the dictionary. After that, we can just invoke todo service delete todo method passing the ID. In this case, we just need to return API get response with empty body and status code of 200. The last handler is the handle list method. In this handler, we just invoke todo service get all todos method. Then transform the result of the todos array into API gateway response, passing the array to be encoded as JSON into the HTTP body, and make sure to set the status code as 200. That's it for the TodoLambdaHandler. Now, let's put this into main.swift file where we will run the lambda passing the handler. Make sure the project can be compiled successfully before continue. We have completed building the app. Now, let's archive the app into a zip file so it can be uploaded to AWS Lambda. Before we begin the process, make sure to install Docker into your operating system. Check the link to install Docker from the description if you haven't installed. We're going to use Docker container using official Swift Amazon Linux 2 image to build our release, package the binary into the bootstrap file required by the AWS Lambda to run the function. Let's follow the instructions from Fabian Fitt's website. He is one of the contributors of the Swift AWS Lambda Runtime library. He posted a great tutorial on building and packaging Swift app into the zip file ready to be used in AWS. I'll provide the link to his website at the description. As we have already completed building the app, we can start from step 5. In this step, we need to create a Docker file on the project directory. So, let's open terminal and navigate to the project directory. Then, create a new file named Docker file. Open it in your editor, then copy and paste from the web into the file. This will use the Swift nightly image for Amazon Linux 2 from official Swift Lang Docker repository. Then add the required dependencies to build and run Swift. Next, let's build the container using the Docker file. Let's give it the name of Swift Lambda Builder. I already built the image previously, so I don't need to download it again. But you might need to wait a little bit longer. So after all the container has been downloaded, let's build the binary from the Docker container using the syntax from the web. Make sure to replace square number to our app name, which is Todo API. This will run the Swift Lambda Builder container and set the current directory as the working directory. Then execute Swift build command passing the Todo API as the product flag and compile it in release mode. Okay, the building of the app has been completed. Now, in the next step, let's create the package for the executables for the deployment. So basically, we need to create a bootstrap file and symlink all the executables. We also need to copy several Swift runtime library into the folder. To help us do this, let's create a script. Create a new folder called scripts. Then inside the folder, create a new shell file named package.sh. Copy and paste the code from the web into the file. Don't forget to set the file as executable using the sudo chmod. Navigate back to the project directory and run this syntax. Run the following command. Make sure to replace the square number with Todo API. Just like before, this will run the Swift Lambda builder container, then execute package.sh inside the scripts folder. We can check the result of the zip package by navigating to build Lambda Todo API. The lambda.zip file should exist in the directory before we can continue. That's it for the packaging. Now let's move on to the next step, where we will use serverless framework to handle deployment of our function to the AWS. To begin, please make sure you have Node.js installed in your system. You can install using the installer from the official website or using Brew Package Manager. After that, you can run sudo npm install -g serverless. This will install the serverless package globally in your system. I assume you have already set up the AWS credentials in your user directory /.aws/credentials. If not, please create an IAM role from AWS console with the required privileges. In my case, I usually provide full access to provision resources in my main machine. To deploy with serverless framework, we need to create a serverless YAML file in the project directory. This YAML contains all the declaration we need to provision the service. Let's create the serverless.yaml file in our project directory. Open it with your code editor. Be very careful with the indentation when editing a YAML file, as it uses indentation to structure the data. It is preferred to use spaces instead of tabs when editing YAML file. In this case, I use 2 spaces for the indentation. At the top, let's declare the service. You should provide your own unique value here. In this case, I name it as elf todo api dev. Next, let's declare the package. Inside the package, we have one key, artifact. Let's put the directory of where our lambda.zip is located inside the build folder. This will be used for deploying to AWS later. Next, let's declare custom key used for referencing resources in this YAML. We'll have one key, which is the todos table name with value of todos and provider.stage value. Next, let's declare the provider. Inside the provider, set the name to AWS and runtime as provided. For stage, we'll set it as dev and region to US West 2. For the environment, we have one variable, which is the to-dos table name. And for the value, we can retrieve it from the custom to-dos table name we created earlier. Next, let's declare the IAM role for the functions. We only provide two IAM roles. One is to write logs to CloudWatch, and the other one is to perform the CRUD operation to DynamoDB. Next, let's declare the functions. We have 5 functions that triggered from HTTP events. First one is create to do. With handler of create, we set the path to /todos, method to post and enable course. Second one is read to do. With handler of read, set the path to /todos/id, method is get. The ID placeholder can be retrieved from the path parameters dictionary in the event request from API gateway. Third one is update to do. With handler of update, path of /todos/id and method of put. Make sure to enable course. The fourth one is delete to do with handler of delete, path of /todos/id and method of delete. The last one is list to do's with handler of list, path of /todos and method of get. That's it for all the functions. Next, we need to provision the DynamoDB table resource. We need to put it inside the resources. Give it a name of to-dos table. The type is AWS DynamoDB table. For the properties, table name value can be retrieved from the custom.todos table name variable. The attribute definition will have one single attribute name, which is used as the key for this table. We are using ID as the key. Finally, set the billing mode as pay per request. That's it for the serverless YAML file. You can learn more about serverless by visiting the website that I provide in the description below. Other than AWS, it also supports deployment to Google Cloud Function and Azure Function. To deploy from the project directory in the terminal, we can just type. This will parse the serverless YAML, create the resources on the cloud formation, upload the code to S3 bucket, provision the DynamoDB table, and handle the creation of API gateway for our functions. Okay, so there's an error in our template. As you can see here in the stack, encountered unsupported function. Okay, I made a typo here. I should use a lowercase n. So let's update this and let's deploy again. Wait until the deployment has completed. As you can see in the output, it provides us the endpoints that we can use to hit our CRUD API. We can also check the deployed AWS Lambda functions using the web dashboard. We can check the status and also the logs of our function from CloudWatch. Try to use Postman or curl to hit the endpoints. So let me try to use Postman to hit our endpoints. First is the get list of to-dos. And let's create a new to-do. And let that do. And update it. And delete it. Okay, so I already provided the project GitHub repository in the description below. If you've encountered an error when following this tutorial, you can refer to that GitHub as the source of truth. So that's it for this video tutorial. To summarize, we have learned on how to build a REST API using Swift, and we successfully deployed it to AWS Lambda using Serverless framework. There are many various other cases that we can explore, such as processing an image when it has been uploaded to an S3 bucket, or maybe processing a notification from the simple notification service from AWS. So, I encourage you to keep learning and building. And I hope this tutorial will be helpful to all of you. So, until the next video, let's keep the life learning goes on. Bye!